Let's take a look at problem 74A from chapter 17 of the Brewis textbook. In this problem over here, they're asking us to synthesize an amino acid, alanine, starting from propanoic acid. Now, this is one of the more complex mechanisms. The summary is up above over here. We're going to do what's called a Hell-Volhard-Zelinsky reaction, and that puts a halogen at the alpha position of a carboxylic acid. Then once we have that, we can react this with excess ammonia to produce our alanine molecule. Let's take a look at this mechanism. We're starting off with propanoic acid and this tribromophosphine compound. Now, bromine's very electronegative. I've got 3 of them over here. So this phosphorus here is actually quite electrophilic. And what's going to happen, the first step here, this oxygen here, delta minus, will go ahead and get sucked into that phosphorus, and this will then go ahead and pull out a bromide. At that point then we have we have a carbonyl, here we go. With the phosphorus, we'll have 2 bromines on the phosphorus, lone pair of electrons still there. Oxygen over here, we still have our OH group over there, and a Br minus came flying out. At this point, this Br minus then is going to get sucked into this activated carbonyl. So here we go for that, and then this will go up over there like that. Now we'll have oxygen, phosphorus, bromine, another bromine, lone pair of electrons there. This oxygen has 2 lone pairs of electrons. We'll have a bromine down over here, the one that came in. We'll have this OH group here, like that. And at this point, we're going to have some intramolecular activity going on here. The oxygen, delta minus, this right here, delta plus, this oxygen right here, the phosphorus is electrophilic because it's got all these things pulling on it, and so that's going to be really the driving force here for this to happen. It's actually strong enough to break a carbon-oxygen bond. So this goes there. The phosphorus then is going to let go of this bromine. This bromine is going to pick up that hydrogen right there, and then these electrons are going to come in over here to reform a carbon-oxygen bond that this one lost. So this one's a little bit kind of complex. I wouldn't expect you to know how to do it without kind of going through it first. At this point then, we will now have our boom, 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 carbon-oxygen double bond. Now this oxygen right here, this one right here was this one right there. We will have our bromine here, and coming flying out, we'll have our POBr compound, lone pair of electrons, and we'll have HBr, because this bromine picked up that hydrogen right there. Strong acid, HBr. At this point then, we have that, so we're okay with that. What else is going to happen? I think something else. Oh, I think I messed up here. Apologies. This oxygen comes over there. This goes over there. I lost that hydrogen. I messed up. Apologies there. Because this hydrogen got picked up. This hydrogen got picked up by that bromine, got picked up by that bromine right there. At this point, we have an acyl chloride or acyl bromide. And these are very electrophilic, and we have the strong acid over here. So first thing that's going to happen is, right, delta minus, this oxygen is going to pick up that hydrogen right there, activate the carbonyl, there and there. And once that carbonyl is activated, and I have a Br minus here, from that HBr, I'm going to show these hydrogens at that alpha position. And the reason why I'm going to show those hydrogens is because now at this point When this oxygen is positively charged, it wants to recoup some electrons, and here we go. Bromide comes in over here, those electrons up there, these electrons over there. I will have regenerate my HBr molecule, and now this will be an enolate. Boom, 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 boom. Oxygen, hydrogen, 2 lone pairs, bromine here, 1 hydrogen at the alpha position. I temporarily have a neutral molecule. At this point, this is an enolate right here. And now the bromine comes in. We also have Br2 in this mixture. So this HVZ reaction, I failed to show all the reagents. It was Br2, PBr3. These were the first steps. So we're still at the first step. At this point over here, this enolate will come down. Let me draw the bromine molecule, which was just sitting around this whole time, not involved because we had things that were more active. So now this will come in and attack one of those bromines and go back. Now remember, bromine is a nonpolar molecule. However, it's electronegative, and so you have the 2 bromines constantly pulling on each other back and forth. So for an instant in time, one of these will be delta plus and the other one will be delta minus. And it's at that instant that the bromine, once it's electrophilic, is like in distress and was willing to get attacked. So now at this point over here, we have, let me see here, I lose track of what's going on. We finally have added something at the alpha position. Lots of stuff going on here. Oxygen, hydrogen, that's one's positive. We have the bromine over here, that bromine right there. We now have the hydrogen, and finally we put a bromine at the alpha carbon, right? This is the alpha carbon right there. At that point, and we have a Br minus, right? This Br minus right here that came out. And now for a moment, the Br minus is going to go ahead and pick up this hydrogen right here. And I will have back to my regular carbonyl, my acyl bromide. Boom, boom. Hydrogen, bromine. Now, we're still not done because we still have this bromine over here. And now this is where the second part of the reaction comes into play. We're going to add some water. So let me kind of, this is not our final answer, but this is the end of step 1. End of step 1. Step 1 right there. Now we go ahead and we start step 2 where we add water. Now I want to remind you that of carbonyls, the carbon of the carbonyl is electrophilic, and if you have a carbon oxygen double bond but also a bromine over here, there's no resonance because bromine's on a different level than oxygen, and this poor carbon right here is very electrophilic because it's being pulled on by the oxygen and pulled on by the bromine. So this is really delta plus plus right there, enough to suck in the water and push these electrons up at first. Now again, a regular carbonyl is not electrophilic enough to suck in water right here, delta minus, but this is. And so now we're going to have, at first, O minus Br, water molecule, oxygen is positive, bromine over here, but then bromine's a really good leaving group, and so this will come back down, kick out that bromide, and we're going to barely have enough room over here. So now we're up to this, looking a lot more like our final product, bromine there, O, H, H, positive, and then finally the bromide that came out, is going to pick up one of these hydrogens right here and give us our final answer, which would be, and actually this is not even the final answer, but for now, that is the mechanism for the Hell-Volhard-Zelinsky reaction. So this is the first part. We're not done yet because we need to do the next step. I'm going to pause, clear the board, and go ahead to the next step, which is a lot shorter than this current one. In the previous segment, we finally did our Hell-Volhard-Zelinsky reaction to alpha brominate, a carboxylic acid. Now, the final step to create alanine is just to react this with excess ammonia. Ammonia is a weak base, nitrogen, delta minus, over here, delta minus, delta minus. This hydrogen right here is delta plus. This is a carboxylic acid. So the first thing that's going to happen is one of these ammonia molecules is definitely going to go ahead and pick up, deprotonate this carboxylic acid to the carboxylate O minus, and over here, and we will have NH4 plus. So that's definitely the first one. But we have excess ammonia, and bromide is a good leaving group, and ammonia is a decent enough nucleophile. Now, ammonia doesn't attack in an SN2 manner if you have a poor leaving group, but if you do have a good leaving group, such as a bromide, ammonia can attack in an SN2 manner. And so this will just go ahead over here and kick out that bromine, and we now have our amino acid. The building blocks of proteins, amino acids connect to form proteins, and we have our NH4 plus, our alanine molecule.